as I mentioned in a previous video, one of the main purposes of college algebra is to learn how to graph functions. In order to do that, it's important that you have a foundation understanding of what the coordinate plane is that we do that graphing in. So the purpose of this video is to introduce the coordinate XY, or sometimes called the rectangular XY plane. And then once we understand the basic terminology that we use when we talk about the XY plane, we'll bridge that into some preliminary graphing concepts. Okay, so the coordinate XY plane. As far as the terminology, the coordinate XY plane consists of two axes. We have the horizontal axis, which we label as the x-axis, and the vertical axis that we label as the y-axis. And they do form a 90-degree angle in relationship to each other. When you think about the plane, there are several concepts that it incorporates. So first of all, we already talked about the two coordinate axes, the x and y. The origin. The origin we will label as where the x and the y axes intersect each other. So this point right here is called the origin of the coordinate xy plane. When we take these two axes and intersect them, we divide this coordinate plane into 4 quadrants. You don't necessarily need to understand this for college algebra about how we label these quadrants, but at other math courses, for example, trigonometry, this would become important. But I'm going to label them either way. So this upper right quadrant is known as quadrant 1. The upper left is known as quadrant 2, lower left, quadrant 3, and lower right is quadrant 4. So you can see that we started in the upper right corner and then we moved counterclockwise around our plane. So those are the quadrants. You may hear words or terminology such as domain or range. The domain refers to the inputs of a function, and the range refers to the outputs. So for our purposes, as we talk about the x-axis, that is labeled as our domain, so any x values that we have, and the range is for the y values. So let me mark the y-axis as our range. Again, we sometimes may refer to it as the inputs and the outputs. Also, you may hear it referred to as the independent variable and the dependent variable. Okay, so once we have our coordinate plane set up, we can actually plot points, also called coordinate pairs. They're labeled as an XY pairing, and I have an example of some over here that we're going to go ahead and plot. What I do want to point out is it is important to associate the labels with positive and negative values. And so for our x-axis, as you start from the origin, if you move to the right, those are positive values, and as you go to the left, those are negative values. So for example, if I were to segment these little squares and make them each worth a value of 1, so I'd have 1, and then this one becomes 2, 3, 4, etc. These are positive values increasing as I move to the right, and these would be negative values decreasing as I move to the left. So I could do that same thing. I could index this at every grid, and then this one would become -2, -4, etc. We would do the same thing with our y-axis. Sometimes you'll see graphs and they're not scaled the same. And what I mean by that is this x-axis, you can tell that I've scaled every grid as a 1. You may see the y-axis scaled differently. What matters is that you're consistent throughout the entire axis. I'm going to go ahead and keep this one the same, and every square I'm going to call a 1, which would mean if I mark this, again, we've got 1, that would be +2, 3, 4, etc. So again, on the y-axis, as I move up, those are positive values, and if I move down, those are negative values. So again, if I mark off each grid. This would be -1, -2, I'll label that one, -3, -4, etc. So when you create a grid system, you get to actually label your axes. I could have made each one of these boxes worth 5 if I wanted to, 5, 10, 15, 20, etc. Again, the important thing is that once you've established your scale for an axis, you need to maintain that scale throughout that entire axis. And then it's very common to have each axis have the same scale, but again, not necessary. I could count each one of these X grids as a 1, and I could have chosen to count by 5s along the Y if I wanted to, for example. But as we get ready to plot these points, it's very important to understand the X is the coordinate that will come first. If it's positive, I will be going to the right. If it's negative, I'll be going to the left from my origin. The Y value comes second. If it's positive, I'll be moving up. If it's negative, I'll be moving down. So again, if we use the origin as our reference point for starting, we can go ahead and plot these points on the coordinate plane. So we're going to go ahead and plot these points. This is the point 0, 0. So remember, the X will be given first, and then the Y. So 0, 0 is that origin point that I referred to. In other words, I haven't moved left or right or up or down. So that first point is right here on the origin. What I've done is I've actually chosen a point out of each quadrant. So you can kind of see what that looks like. So here, the X is a +2 and the Y is a +4. So the X being a +2 means I move to the right by 2. And then the Y being a +4 means I'm going to move up by 4. So if I mark that point, again, right 2 and then up 4, that lands me right here. So when both our X and Y are positive, we end up with a point in quadrant 1. The second one, the X is negative and the Y is positive. So starting at my origin, I'm going to move 3 to the left and then 3 up. So 1, 2, that's 3 to the left, that's a -3. And then 3 up. That puts me right here. And that point happened to be in quadrant 2. And I will label these. So that was the point 2, 4. This was the point -3 and 3. Okay. Now the fourth point. X and Y are both negative. That's going to actually put me down here in quadrant 3. So the X is -1, so I go 1 to the left, and the Y is -4, so I'll go 4 down. So again, starting at the origin as a reference, -1, and then 1, 2, 3, 4. That places me right here. So that is indeed in quadrant 3. And then finally, my last point, X is positive, Y is negative. 6 to the right, down by 2. So starting at the origin, 6 will be right here, and then down 2. So that puts me right there. So this was a really quick and simple exercise in point plotting once we have our coordinate plane established. So why do we do this? Well, college algebra, again, is a lot about graphing. We want to be able to graph equations, and some of those equations will be, many of them will actually be functions. The problem is this: you don't want to have to point plot all of the time. So when we have an equation that we want to graph instead of points, when you first start your algebra journey and learn about plotting, you most likely do what's called point plotting. And this is an example of a linear equation. It's linear because I will have 2 variables. It's a linear equation in 2 variables, X and Y, and they're both to the first power. When we have variables to the first power, we just don't choose to write the exponent. It could be considered redundant. But this is a linear equation using 2 variables, which will then plot on the 2 variable coordinate plane. So one way that we learn how to do that, again, is called point plotting, which means we're going to choose some X's. We are going to stick those values in one at a time for this independent variable or the input. and see what y pops out. And then we'll pair those up. They will become coordinate points and we will plot them. And then basically we're going to connect the dots. So what do we pick? Well, when you're graphing a linear equation, typically the expectation is that you need to choose at least 3 values for x. That way, once we have those 3 values chosen and we plug them in and we plot those points, it should look like a line. That's what happens when we graph a linear equation. It looks like a line. So if it doesn't look like a line, then we've made a mistake somewhere. If we only plotted 2 points, they would always look like they formed a line and we wouldn't know if we made a mistake. So at least 3 points. So what do you pick? Well, we can pick really whatever we want because there aren't any domain restrictions here for this line. Maybe we choose a negative value, 0. It could be a good one to pick. That would make the math easy. And a positive value. So how about we choose an x of -1, 0, and 1. Those are 3 distinct x's, and if I plug them in one at a time into this equation, I can determine what y is. Okay, so plugging in -1. First, let's write the equation. I'm going to leave a open space here. This is where I'm going to plug in the value for x I've chosen. So we have a -2x plus 4, and we are going to plug in -1. If I compute this math, -2 times -1, that's a +2. Negative times negative is positive. And then plus 4. So I actually have 2 plus 4, which is 6. So that I can see when I choose an x of -1, the y value that spits out is 6. And so this actually becomes a coordinate pair or a point. X is -1, y is 6. So let me write that down here. I can repeat that same process using an x of 0. So we would plug a 0 right there. And then finally an x of 1, and I'll get the appropriate values for y that go with those pairs. So if I plug in a 0, we can see -2 times 0, that term would actually, that piece of it would go away. So I have 0 plus 4, which is 4. And then the third, if I take an x equals 1 and put right there, -2 times 1, that's -2 plus 4, -2 plus 4, that is a +2. So again, these become 3 points I can plot on my grid. -1 and 6. So -1, that's 1 to the left, up 6. That puts me right there. You can see that. 0, 4. So I'm not going to go left or right at all because x is 0 and the y is 4. So I will go up by 4. And the third one, when x is 1, y is 2. So I will go over +1 and up 2. And we can see, again, this is one of the reasons why we choose at least 3 points. This definitely looks like it forms a line, which is what I was expecting. So I'm fairly confident that I've probably done this correctly. Again, this is what I meant earlier. If these 3 points didn't form a line, like maybe we had this over here and, you know, this up here and then something down, that would tell me that something was wrong and I would go back and recheck my work. But this looks pretty good. Okay. So this is an example of using point plotting to create a graph. This is the challenging piece though. Is point plotting the best method or the best approach? If we have a simple function like a line, this wasn't bad at all. But as we will show as you progress through the college algebra course, we can get some pretty interesting looking functions, and point plotting is probably not the way we want to go to do the graph. Could we do it? Yes. Would it be efficient? No, probably not. So some of you in your previous algebra studies may have learned an alternate way to plot a line. You may have started by doing point plotting, but then you are quickly taught this graphing method called slope-intercept. It actually can be a much more efficient way to graph a line. So if you have a line that's in slope-intercept form, y equals mx plus b, that may ring a few bells, y equals mx plus b. If we know our y-intercept and our slope, we simply graph those things and then we can create the line that way. And if an individual had chosen to take that approach with this line, they would have created the same exact graph. And so that is an important concept to understand, because as you progress through your college algebra course, what you're going to realize is that functions can get pretty complicated. And point plotting is probably not the preferred method of choice. We have alternate graphing methods we're going to learn, and those methods may be specific to the actual type of function we're trying to graph, which is why it becomes important that you start to recognize which functions are which. So if you look at, I have 4 different equations written down here. They all do happen to be functions. It's not necessarily important at this point that you understand what type of functions they are. I will introduce that though. This first one, this happens to be a quadratic. This second one is a polynomial function. This third one is a rational function, and this fourth one is a radical function. Again, it doesn't matter at this point whether you could classify these. You'll learn how to do that in this course. What matters is, would you really want to point plot these if I asked you to go create those graphs? Now, the quadratic, maybe not so bad. I could pick some values for x, plug it in, and see what spits out for y. But as you look at these other equations, they can get a little bit complicated. I don't know that I would want to sit there and try to choose values for x to plug in and hope that I could figure out what that picture looks like. We talked about when you have a line, the general expectation is that you have to choose at least 3 x's. Well, the more complicated these functions get, the more x's you have to choose. Do you choose 5? Do you need to choose 7? Do you need to choose 10? How many x's is enough? And then furthermore, what x's should you even pick? Maybe there's domain restrictions. Maybe there are x's that aren't allowed. And so you have to go through this process of what's allowed, how many do I need? It can get very tedious in a hurry. And so you start to really understand and appreciate these alternate graphing methods that you're going to learn. And in conjunction with that, there's some new terminology. So some of these may sound familiar, none of them may sound familiar to you, but as you progress through this course, you're going to learn about x and y intercepts and how to find them, what a vertex is and how to find it, end behavior, asymptotes, transformations, which could include concepts such as shifting, reflecting, stretching, shrinking. This all may sound new right now, but as you progress through this course and you learn how to graph these different types of functions, these terms will become very familiar to you and much appreciated, again, as you learn an alternate graphing method that takes you away from point plotting and allows your graphing experience to be much more efficient and accurate. So again, that's one of the main goals of college algebra, is to graph functions, and hopefully this gave you a reminder of the background that you should have seen before, which is the whole concept of the coordinate plane and how we can use that tool to create graphs for functions.